All right, let's get started. Okay, so sign-in sheet is going around. A couple things. So your homework 2 has been assigned today. Okay. Now, after today's lecture, you'll be able to tackle just about all of it. I think the last 2 problems will be sort of up in the air after today's lecture. But after Friday, basically after Friday, you should be able to tackle all of it. Like for instance, like problem 1 is a cracking moment problem. You can do that now. So there's 5 problems. 4 of them come out of the book, and then the 5th one is one I came up with on my own. You'll have a little bit of fun with it. So. Oh, it's not that bad. Now, today what we're going to do is we're going to take this cracking moment concept and we're going to take it and move forward with it. So up until now, we've been asking ourselves, well, how much moment causes a beam to crack? Now what we're going to do is we're going to ask ourselves, well, what if the cracking moment is 25.6 foot kips and you put 80 foot kips on it? How do you handle that? Okay. So how do you handle the analysis of a reinforced concrete beam, or how do you determine stresses once the beam has cracked? And in order to do that, you'll do a transform section analysis. So that's really what we're going to focus on today. It's not that hard, but you kind of need to know the cracking moment and the moment of inertia stuff first. So I think you'll see where this all sort of ties together. Okay. So this was what we worked on last time. So we had a T-beam that was subjected to a moment. And we were not only that, but we were determining if these are the properties, how much moment can it withstand before it cracks, et cetera. But one of the big things I want to highlight is the difference between example 2 and example 3 was the use of the parallel axis theorem. Example 2 was really just, here's the moment of inertia, BH cubed over 12, have a good day. But in example 3, the actual computation of the centroid, the computation of the moment of inertia, there's something to that, okay? And there was a reason for going through that review process because of this, because of looking at the concrete beam in its cracked state, okay? So what we're talking about now is what I'm calling stage 2 of a concrete beam's behavior. So stage 1 is when we're talking about really, really low levels of load. Really light levels of load to where the tensile component of the concrete beam has not experienced cracking yet. So we're really just dealing with regular old mechanics of deformable bodies, sigma equals my over I, and basic stuff until your tensile stress reaches FR. Now, what happens after that? Okay, well, what happens after that is the concrete has experienced cracking. Okay, so we have to handle that. One of the ways that we handle that is we make a blanket assumption right off the bat. And we say, all right, once we have exceeded the cracking moment, we are going to make the assumption that every single bit of concrete that's in that cross-section that is experiencing tension is ineffective. Doesn't do us any good whatsoever. So anything that's in tension, gone. Okay? So what we're dealing with is we're dealing with a concrete beam, like let's say this is where the neutral axis is. Anything below that neutral axis that would be experiencing tension, it's gone. Okay? So the only thing we have left, if we're talking about this realistically, the only thing that we have left in our concrete beam cross section is we have, sort of a component of the beam up here that's experiencing compression, and then we've got some rebar down here. I mean, yeah, there is, the cross section does look like this. But that part of the cross-section would be experiencing tension, so we assume it's ineffective. We assume it's cracked. So all we have is concrete in compression, and we have steel. Now, the problem with that is this. The problem is, in order to perform analysis, in order to use sigma equals my over I, in order to compute a moment of inertia that makes sense, we got a little bit of a problem, okay? This cross-section that I've drawn over here on the left, this is concrete. This is steel, okay? There is a beam that is comprised of 2 different materials, okay? All that beam theory stuff, all that sigma equals my over I and all that theory assumes that the beam is made of one material, okay? So how do you take that stuff that we've been using in structural analysis and mechanics of deformable bodies, how do we take all that stuff and apply it to this situation? That's a little complicated, okay? Well, the way that we do that is we use what's called the transform section method. And basically what that means is this. We take this steel and we transform it into an equivalent lump of concrete, okay? So, and we do that through the use of a modular ratio. The modular ratio is abbreviated as the letter N. So let's just keep this simple. Let's say my modular ratio is 10. Let's say it's 10, okay? And that's actually a pretty reasonable value. Modular ratios tend to be like 8 or 9 or 7 or something like that. That's tend to be what they be. So let's keep it simple and let's say it's 10, okay? If my area of steel is 3 square inches, so let's say we're dealing with this beam and I've got an area of steel of 3 square inches. If my modular ratio is 10, what I would do is I would replace that 3 square inches of steel with an equivalent lump of concrete that has an area of 30 square inches. So the idea is that steel is a lot more stiff than concrete, so in order to perform that replacement, you got to have a lot more concrete to replace with that equivalent area of steel. Does that make sense? So the idea is to do an equivalent replacement. Yes, sir. Yes. That, I mean, because, yeah, we're replacing it with an equivalent lump of concrete, but we're talking about that theoretically. Do you see what I mean? It's not like I'm going in there with a jackhammer and actually replacing that steel with concrete. I'm saying I'm replacing this with an equivalent numerical value that has an equivalent stiffness. That's all I'm saying. This is just an analytical technique. Does that make sense? Okay. All right. Now, what gets a little interesting about the transform section method is actually where the neutral axis is. See, if this is a rectangular cross-section, you would think, oh, well, if this is 20 inches tall, that's just 10 inches. And the answer is no, it's not. Because once it's cracked, the equilibrium has sort of shifted a little bit, and you have to do a little bit of a separate analysis to figure that out. And the centroid is not, h over 2. Basically, it's where sum of moments equals 0, and that's not necessarily the same thing, and that'll become clear when we go through the math here in a little bit. So we're gonna take our time with this. I want to look at this example, and what I want to do is I want to calculate the bending stresses using the transformed area method, assuming that this beam is comprised of 3 KSI concrete and it has a bending moment of 70 foot kips subjected to it. So I guess the first question that we need to ask right off the bat is, do we even need to use the transformed area method? And what I mean by that is, well, what if the cracking moment is 120 foot kips? Just use sigma equals my over I and have a good day because it hasn't cracked yet, okay? So maybe the first thing we ought to do is determine whether or not it's cracked. So I'm going to do that very quickly because I think we got enough experience in here with cracking moments that everybody's okay with that. So don't worry, we'll take our time with it. All right. Ooh, that is big. Okay, so this is our beam. Whoop, didn't mean to do that. And we're looking at example 4. Okay. Now, a couple things. Remember that for this beam, FC prime is 3 KSI, or 3,000 PSI. And remember that the applied moment is 70 foot kips. So that's 70 foot kips. Imagine if this was a simply supported beam with so many pounds per foot on it or so on and so forth, and you draw your shear diagram, draw your moment diagram, so on and so forth, and that maximum bending moment is 70 foot kips or what have you. That's how much moment we are putting on the section, okay? And what I want to do is I want to determine first off whether or not it has cracked, and if it has cracked, how do we handle that, okay? Make sense? Everybody okay with that? So first thing I'm going to do is I'm going to determine the cracking moment over here. Now, does anybody remember the formula for a cracking moment? right? So that's our cracking moment formula. Now this is normal weight concrete, so we're just going to say lambda is 1. So if lambda is 1, help me out. What is FR? It's 7.5 times lambda times the square root of FC prime, right? Now how do you do FC, like what do I do here with FC prime? Put in PSI, you get out PSI. So if you put in 7.5 times 1 times the square root of 3,000, you end up getting about 410.8 PSI, right? Okay. The moment of inertia, this is still a rectangle because we're doing a cracking moment. We're just trying to figure out when it's going to crack. So that's just going to be BH cubed over 12, and that's going to be 8,000 cubic inches. I'm skipping through some of the calculations because, I mean, I think this is pretty plug and chug. It should be pretty straightforward. Oh, inches to the fourth, sorry. Inches to the fourth. And then our Y sub T is 10 inches. All right. I went through that kind of fast, but is everybody okay with that? Okay. All right, so therefore, you take FR times IG over YT and then convert your units. When it's all said and done, you're going to get a cracking moment of about 27.4 foot kips. It's YT. Well, that's what I'm saying. You tell me. YT is the distance from the centroid to the extreme tensile fiber, and this is a rectangle, so that's just half your height. Everybody okay with this? So tell me what this means. That's the math. Tell me what it means. It's already cracked. This is how much the beam can handle before it cracks. So it'll be fine up until 27.4, and then it'll experience cracking. We're putting 70 foot kips on it. So it's cracked. So the beam is cracked. So that's what this means. So we'll say M is greater than MCR. Beam has cracked. All right. Sound good? Okay. Now, okay. So because the beam has cracked, we are in transformed section world. Okay. In order to do a transformed section analysis, the first thing that we need to compute is a modular ratio. That letter N I told you about. Remember I said modular ratios usually kind of be like 8 or 9 or 10 or something like that. Okay? Now, what a modular ratio is, like what it actually is it is generally defined as the modulus of elasticity of the stronger material or the stiffer material, I should say, divided by the modulus of elasticity of the more flexible material. So for our case, what that means is we're going to take the modulus of elasticity of steel divided by the modulus of elasticity of concrete. That's what the modular ratio is. Okay, so we got to determine what each of those are. So first off, what is the modulus of elasticity of steel? 29,000 KSI. I told you I wanted that number burned into the back of your head when it is all said and done. So that is a constant. The modulus of elasticity of steel is always 29,000 KSI. Okay? Now, what is the modulus of elasticity of concrete? Look. What's that? No, that's its FC prime. When I ask, like, what's the modulus of elasticity of concrete, that's kind of a trick question because there is no number. You have to calculate it, okay? Say that again. There we go, 57,000 times the square root of FC prime. Let me refresh everybody's memory on that. So I'm going to go back to slide 56, okay? This is slide 56, okay? And this is how we determine the modulus of elasticity. Remember, concrete is a very nonlinear material, right? The stress-strain curve sort of goes like that, right? So remember, what is the modulus of elasticity? It's that initial slope, right? Well, based on the FC prime, the initial slope changes. So we have an equation that we use to compute that. Now, the upper equation is more generic, more generalized for any concrete of any unit weight. But if we're dealing with normal weight concrete, the modulus of elasticity is simply 57,000 times the square root of FC prime. So I propose that, going back to our example, and I tell you what, I'll even be nice, and I'll say slide 56. I'll say that E concrete is 57,000 square root of 3 KSI. No, I was making see if everybody's paying attention. All right. Erasers are expensive, Dr. Mike. Come on. And somebody's like, I'm writing in pen, thank you. All right. 57,000 times. Now, let's be clear. You put in PSI, you get out PSI. This is going to be a big number, so don't let it scare you. In fact, let me sort of write this out. What's it come out to be? And 0.18, what? What are the units? PSI. So, oh, what happened there? I didn't. PS. So, that's in PSI. What is it in KSI? Just move the decimal point over. So 3122 KSI. So if I calculate my modular ratio, so therefore my N is 29,000 KSI divided by 3122 KSI, what does that come out to be? First off, what are the units? There are none, yeah. So what do we get as a number? 9.29. Do I have a second on that? Okay, all right. Good. All right, settle down, settle down. Now when, all right, settle down, settle down. All right, now when you do when you compute a modular ratio, and when you use a modular ratio for computation purposes, it is conventional to round your modular ratio to the nearest whole number. You'll never really see many engineers using 9.29. Really what we'll be doing is just saying take N to just be 9, just to keep it simple. So modular ratios, or modular ratio values, just nearest whole number. So we'll just take that to be 9. So far, so good? Okay. All right. Does everybody have everything on this slide? Okay, I'm going to move on to the next panel. Okay, so now we can start looking at our transform section. Bless you. All right. Okay, now, a couple things to write down. We have our modular ratio of 9. And anybody remember what the area of the steel was? 3 number 9, so 3 square inches. Sound good? All right, so here's my original beam, okay? I'm going to draw it out. I'm not going to be lazy this time. So here's my original beam. This is 12 inches. This dimension is 17 inches. And that's where the steel is, right here. So that AS is 3 square inches, right? Okay, now, we've applied a moment, and that moment has exceeded the cracking moment, okay? So what I propose is that this is what's going on. Okay? This is what I propose is going on. All right. So here's my beam. Everything that is above this neutral axis is fine. Okay? So this dimension is 12 inches. Okay? And this dimension here, I'm going to be honest with you, I really don't know what that is right now. So I'm going to call that X. Okay, we're going to figure out what x is here in a second. Okay, so now normally what I would have is I'd have just some rebar right here, but I am going to replace that rebar with an equivalent lump of concrete. Okay, now I'm drawing this as really a thin rectangle, but really what I'm saying is I have a singular value of concrete right there. Okay, now let me ask you this. We don't really know dimensions of this rectangle because the dimensions don't really matter. But one thing we do know is the area of this rectangle. What is the area of that rectangle? Nope. 3 times 9. This is NAS is 27 square inches. Does that make sense? You're transforming that steel into concrete. Make sense? Now, let's make sure we're clear on some other things. Okay? What is this dimension right here? That is 17 inches. So my question, what's that? 17 inches minus x. Does that make sense? You need to be able to create that in order to, you need to be able to define that in order to determine where the neutral axis is. That's going to be kind of important. Make sense? Okay. Yes, sir.
Is that a dashed line that's supposed to be going through the centroid?
Well, here's the thing. Yes, but that doesn't mean it's halfway up. Okay? That's why I'm not saying that. Okay? Because it's cracked, like how tall was the whole thing? Was it 20 inches? It's not 10. Okay? X is not 10 inches. So, all right. Sound good? Okay. Now, in order to determine the location of the neutral axis, what I'm going to do is I'm going to sum moments. Okay? So, why don't I do this? Why don't I just call this, I'll call this the neutral axis. So, call it the neutral axis. And I'm going to sum moments about the neutral axis. Okay? Now, I'm going to go ahead and write here that all my units are inches. I can do better than that. I'm going to write, because I'm going to be a little fast and loose with my units, but it's all going to be in inches. Okay. Now, let me explain what I'm doing here. Okay. I am trying to determine what this value of x is. And I'm going to do that based off equilibrium. Okay. In other words, I've got this neutral axis. Okay. I propose that that neutral axis has to be at that magical location where the moment contribution provided above the neutral axis has to be equal to the moment contribution provided below the neutral axis. Okay? And let's just sort of take this one step at a time. Basically, what I'm doing is just areas and distances. This is a lot like a centroid. So let's take this this neutral axis. Let's start off by looking above the centroid. So an area and a moment arm. What is the area of the box above the moment, or above the neutral axis? 12x, okay? 12x. So 12x. Now, how far is it from that box, the centroid of that box, to the neutral axis? X over 2. So if we're basically saying area times moment arm, this is a lot like finding a centroid, right? You know, sum of AX over sum of A. It's basically the same thing. So 12x times x over 2. Now I propose that that moment contribution must be equal to the moment contribution provided below the neutral axis. So the same question. What is the area of the box below the neutral axis? 27. Okay? Now that's 27. What is the moment arm from that box to the centroid? 17 minus x. Does that make sense? If you understand that, then everything from here is just algebra. Okay? Yes, sir?
Are we excluding the concrete that was around steel?
That's what I'm saying. everything below, so the question was, are we excluding all that other concrete? The answer is yes, because all of that concrete is in tension. It's cracked. So think about it like this. Imagine bending a beam and there's a crack in it. It's like there's only half a beam. Yes, exactly. So you're not doing anything with it. Yes, sir. Exactly, because what is this? It's the steel. That's where it is. That lump of area is 17 inches from the top of that beam. It's right there. So we're basically just taking that and replacing it with an effective lump of concrete. But all that concrete surrounding it is gone. Does that make sense? Any other questions? This is good stuff. Everybody good? Okay. Now, if you get to this point, then, I mean, this is bringing it back. So on the left side of the equation, I got 12x times x over 2. So that's 6x squared. So we got on the right side, we got to do a little bit of, foiling that, or not foiling, but got to distribute that out. So what's 27 times 17? 459 minus, so 6x squared plus 27x minus 459 equals 0, right? X equals negative b plus or minus the square root of b squared minus 4ac over 2a. You should be able to quote that. Oh, you know what that is. What?
Go on YouTube and look up the song Two Kids. They rap it.
Oh, okay. I'll have to look that up. Okay, now, this is a quadratic equation, right? So whenever you have a quadratic equation, you achieve two solutions for x, right? So therefore, there's an x1 and an x2. So help me out. What are the two values you're getting for x? 6 point, what are you getting, like 781?
Yeah.
What are you getting for the next one?
Negative 11.280.
281?
Yeah.
Do I have a second on these values? Is everybody okay with solving quadratic equations? Now, what do? Exactly. When you do this, you will always achieve one positive answer, one negative answer. The negative answer, disregard it, because it's just a result of the solution of a quadratic equation, but it doesn't make any sense. So just eliminate it. Make sense? No. Yeah, I'm fine. It's my job to get y'all to crack up every once in a while. I mean, that was on purpose, but there was a delay, guys. Okay. Now that we've determined, all right. Now that we've determined where the centroid is, the moment of inertia calculation is actually pretty straightforward. It's a lot like what we did with that T-beam, but it's a little condensed because we don't need, if you remember with the T-beam that we did previously, we had to figure out where the centroid was. Like we had to do the A, the Y, the AY. We don't need to do that here because we know where the centroid is. It's 6.781 inches from the top. So we're going to compute a moment of inertia, but the table's going to be a little smaller. So we're going to have a shape. Okay. There are only two shapes in this cross-section. There's the concrete, and there's the steel. Okay. We're going to have a moment of inertia. We're going to have an area. We're going to have a distance. And we're going to have an I naught plus AD squared. All right? That's what our parallel axis theorem states. Okay? So we're going to take this one step at a time, and I think you're going to find it's pretty simple. Let's just do the concrete start to finish. Okay? So, let's look at the concrete. I have a rectangular component of concrete that is 12 wide and x tall. So, how do I determine the moment of inertia of a box that's 12 by x? So the 12's canceled, so what's 6.781 cubed? Sound good? What is the area of a box that is 12 by x? Just 12 times x. So what is 12 times 6.781? Okay. Now, the D. Remind me what that is. If I remember correctly, I think that was the distance from the centroid of the whole thing to the centroid of each individual shape. So let me just ask this. How far is it from the centroid of the whole shape to the centroid of that box? Where is the centroid of the box? What's it about, like, maybe like right here? No. This distance right here, that is x over 2. So how far is it from there to there? It's just x over 2. So 6.781 divided by 2, what do we get? 3.39. We'll just keep it simple. 3.391. All right. So help me out. I plus AD squared, what are you getting right here? One, 2, 4, 7.5. Have a second on that? Okay. Sound good? Now let's handle the steel. Now we're going to do some. We'll skip the moment of inertia one real quick. All right. What is the area of that box? No, it's 27, right? Remember? So NAS is 27. How far is it from the centroid of that box to the centroid of the whole thing? 17 minus x, so 17 minus 6.781. So 17 minus 6.781. That's going to get confusing. Hold on. 17 minus. What does that come out to be? Okay. The only thing left is the moment of inertia. Remember, okay, this isn't like a box with specified dimensions. I just draw it that way for clarity, but really what this is just a lumped value of 27 right there. That box has no width. It has no height. I just draw it that way for simplicity. What I'm getting at is that box has no dimensions. We take its moment of inertia to be 0, okay? But you're like, well, then why do we care? Like, why do we even count it? Because it's not just the moment of inertia. It's I plus AD squared. So the stiffness contribution from that for that moment of inertia is not from the I value, it's from the AD squared. So what's AD squared come out to be? So we'll just 2819.5, something like that. Now, there's a little bit of rounding differences here. Like if you do this like in Excel, you'll get like about one number off or something here or there, but that's no big deal. AD squared. So if I sum all these up, what do I get? The I plus AD squared, like right here. 4067.1. Is there a second on that? I propose then that the moment of inertia, and I'm going to call this a transformed moment of inertia, is, bless you, 4067, we'll just keep it that way, inches to the fourth. Yes, yes. Yeah, it's basically just saying this is a lumped area at that one particular point. Like it's just a value, an area value right there. But it doesn't have any dimensions, which is why we take that to be 0. That's a good question. Yeah, right. No, down here. Yeah. I'm just keeping it simple, yeah. Any questions? Any questions? Everybody good? Okay. All right. I'm lazy, so I am going to redraw this. Or I'm going to, let me erase this part. No. What we are going to do is calculate stresses with this cross section. Okay? You'll see what I mean here in a second. All right. Everybody got this? All right. Okay. What we need to do is we now need to compute bending stresses. Because, I mean, that's what the problem's asking. We need to determine bending stress. Okay. Now, so remind me, how much moment did we apply to the section? 70 foot kips. Now, just to keep things simple, I'm going to convert this into inch pounds. Let me ask you this. How would I convert foot kips to foot pounds? What would I do to it? No, well, that's foot kips to foot pounds would be 1,000. Foot kips to inch pounds would be 12,000. Yes. So let's do this slowly. I think. How about this? Would you agree? Hold on, everybody watch it. Everybody watch it. Would you agree that with this? Would you agree with that? Okay. Would you agree with this? Do you agree with that? Just take the foot multiplied by, or the kips multiplied by 1,000 to get pounds. Take the foot multiplied by 12 to get inches. So foot kips to inch pounds. Everybody okay with that? Oh, now, you didn't have to point out my handwriting deficiency in front of everybody, but, you know, thanks. I have my own post-traumatic stress. I think I'm blaming the screen a little bit on that one. It's kind of tough. Okay, so just writing down a couple other values. So the transform moment of inertia, that's 4067 inches to the fourth. And what was x? 6.781. Okay. All right. Okay. Now, I'm throwing this bending stress calculation in there just so everybody gets accurate values. So now that we've done the transforming component of it, we can now use sigma equals my over I. We've got to be a little careful with the steel component. So I propose that, first off, let's deal with the concrete. That the bending stress in the concrete, the maximum bending stress, is just my over I. Now what I'm going to do is I'm going to say that's m divided by the moment of inertia times y. But let me ask you this, what's the y? How far is it from the centroid to the tippy top of the section? It's x, right? From the centroid to the very top, that's x. So that's why I'm saying that this is mx over ITR. Is everybody getting that? Okay, so we have 840,000 inch-pounds times x is 6.781 divided by 4067 inches to the fourth. So what does that come out to be? Like, we'll keep it to the nearest, like, whole number. Just keep it simple. 1,400 even? So we'll say 1,401. 1,401 what? PSI. Sound good? That is the maximum compressive stress that this concrete is seeing. What's its maximum compressive stress? Like, what's the maximum compressive strength of the concrete? Anybody remember? What's FC prime? 3,000 PSI, right? So think, this beam has gone well beyond the cracking moment. You think it can still keep taking load? Of course it can, right? I mean, it's still not even there yet. So just something to keep in mind. Now, so let me ask you this. What would be the stress in the steel? How would you do that? My over I. What is my over I? Tell me what to write. You tell me. M's going to be, it's the same moment, right? What's the Y? Now somebody else. What's the Y? 17 minus X over ITR. Does that make sense? Okay, now I need everybody to pay attention to this. This is important, okay? This equation still assumes that this is concrete. But in reality, this is not concrete. This is steel. So in order to bring it back to where we're dealing with steel, we got to multiply by n, okay? So that's sort of the caveat, just so everybody's aware of that. So we have 840,000 inch-pounds times 17 inches minus 6.781 inches, then multiply by 9 divided by 4067 inches to the fourth. 18,995. So 996. Do I have a second on that? Okay. So therefore, the stress in the concrete is 1401 psi, and the stress in the steel is 18,996 psi. I'm saying what, go ahead.
That'd be like the maximum that each one can take. So even if your concrete gives, your steel's still there, right?
Well, let me elaborate on both your questions a little bit. You're asking like what this means, okay? So first off, what I'm presenting to you is these are the stresses that the beam is experiencing under this moment, okay? What I'm really trying to do with this example is make a point, okay? What's the maximum stress in the steel? 18,996 psi? When does grade 60 steel yield? No. That's its Young's modulus. When does grade 60 steel yield? 60,000 psi. So let's think about this, okay? This is well after it's cracked, but the steel can keep on going for a long time, right? So I guess what I'm really trying to convince you of is the cracking moment, the maximum capacity of a steel beam, it's not even close, okay? The concrete can keep going and the steel can keep going, okay? That's what I'm trying to convince you with this example. Everybody okay with this? Any questions? Yeah, okay, all right.
What's the significance of the cracking moment
That's a good question. All right. I'll give you two quick answers. The question is, what's the significance of the cracking moment? The first significance is that the cracking moment is what we will use later in order to determine what's called an effective moment of inertia. And that's what we use for deflections. The idea is that some of the beam is cracked, some isn't, so you use sort of a weighted average approach. The second reason is, like, especially in pre-stressed, the cracking moment and the cracking stress is used for serviceability limits. But for us, we'll use this later in deflection world. So that's would be my best answer. Yes, yes, sir.
So in this situation, the steel is taking on 18,000 psi and the concrete's taking 1401.
Yes.
So the steel accounts for that much of its strength. Is that how it
Oh yeah. No. I mean, you got to understand, you have this big bulky beam of reinforced concrete, and its compressive strength is only 4,000, 3,000 psi. Steel by itself has a yield strength of 60,000 psi. So that's just sort of the nature of the material. But the idea is you don't need that much steel. You see what I mean? All right. Yes, sir.
So who did this problem without the steel in it? Isn't already smithereens, right?
Oh, if you put this moment on a beam, and that beam was on a bridge that was holding up your grandma going to the post office, your grandma's in the river. Like, we assume that no, grandma can't swim. Okay, everybody, hold on. Hold on. We're not done. All right. Okay. Do you agree that on example 4, that beam can take a whole lot of load? Okay, so I guess the question that we ultimately need to ask is, what is the ultimate strength? All right, guys, settle down. All right, what is the ultimate strength? In other words, what is the absolute maximum load that a reinforced concrete beam can take before it is gone? Okay, before it's gone. Okay, now, that is actually not that easy to address when you consider the following. Go back some. These are stress-strain curves for regular concrete. They are very non-linear, right? Remember your bending stress profile for beams? Remember how it looks something like this? But we're talking about stresses at the absolute ultimate state. So I propose that if we're talking about right when the beam is going to fail, the stress profile is nonlinear. So how do you determine the capacity of a beam with a nonlinear stress profile? That's not easy. We recognize it's not easy. We have a shortcut. A shortcut I'm going to show you on Friday. Let me sort of explain something. Friday's lecture, what we talk about, the Whitney stress block approach, honestly is one of the most important lectures we will have in this course period. So be there. It's kind of important, okay? I am going to break out the C word a little bit calculus, but it ain't that bad. Ain't that bad. That's all I got. I'll see you all on Friday.